Okay, so let us start with our next final definition in damped vibration. Definition of the quality factor of a damped vibration. So we would like to define the quality factor of a damped harmonic oscillator. So when we are talking about the quality factor, the specific questions that one comes across is to define quality factor. We have to deduce an expression for it for a mechanical oscillator and electrical oscillator. And okay, so basically let us do these two, address these two questions, okay, for quality factor or Q value. As you realize, this is a very important observation for a damped oscillator. Now, well, the quality factor or the Q value measures the rate of decay of energy of damped harmonic oscillator. Now, for an undamped harmonic oscillator, do you remember the expression for the total energy? The total energy, what is the total energy for an undamped simple harmonic oscillator? For an undamped simple harmonic oscillator, what would be the total energy E? If you remember, it is equal to half of m omega 0 square a square, isn't it? That is the total energy. Half of m omega 0 square a square. Now, in case of damped oscillation, what happens? The work done against the retarding or resistive force is not stored as potential energy. As a result, as the particle oscillates, the total energy goes on decreasing. So, the amplitude of a damped oscillator, as you have seen just now, it is equal to A0 e to the power minus kt. Okay, and the omega 0 of a simple harmonic oscillator is replaced by omega prime, which is equal to square root of omega 0 square minus k square. Okay, so that is your omega prime. Alright, so the energy of a damped oscillator, what is it? If you just make mere substitutions, okay, the energy of a damped oscillator, what do we get for the energy of a damped oscillator E? Obviously, it will be equal to half of m omega prime square omega 0 square e to the power minus of 2kt, isn't it? So if you just take m omega 0 a0 square, okay, if you just take m omega 0 a0 square, well, then what can you say over here? You can say that this is equal to E0, because if you take E0 as, if you consider, okay, E0 as half m omega prime square A0 square, then you can tell that this is equal to, this is equal to E0 e to the power minus 2kt, isn't it? You can say that. All right. Now, what is T? When T is equal to, suppose say, when T is equal to 1 by 2k. All right. When T is equal to 1 by 2k. Suppose if you take t equal to 1 by 2k, then what happens? Then E is equal to E0 e to the power minus 1, which is equal to E0 by E. Alright, so what can we conclude from here? That at time t equal to 1 by 2k, which is equal to 1 by 2. What is 1 by k? It is tr. 2m by r, which is equal to m by r. So after a time t equal to m by r, what is r? R is the damping constant. What is m? M is the mass of the oscillator. What can we say? When t is equal to m by r, the energy of the oscillator decays to 1 by e of its original value. When this is the case, then the energy E is equal to E0 by E. Do you agree? Now during this time, how much will the oscillator move? Now during this time, how much will the oscillator move? During this time, the oscillator will move through an angle theta. So theta will be equal to the oscillator moves through an angle theta, isn't it? Then what can you say about theta? In that case, then theta will be equal to omega prime t, which is equal to omega prime m by r, isn't it? So that is the quality factor Q. Q is equal to omega prime m by r, or the Q value. This is the Q value. It is defined as the angle in radians through which the damped oscillator oscillates as the energy decays to 1 by E of the original value. Okay, now this is equal to omega prime. What is m by r? 1 by 2k by 2k, isn't it? Now in case of what can we say about an electrical oscillator? What is 2k equal to for an electrical oscillator? For an electrical oscillator, 2k is equal to what? It is equal to r by L, or k is equal to r by 2L. So Q for electrical oscillator, Q for mechanical oscillator is this. Q for electrical oscillator is equal to omega prime L by R. This is very important. Okay, all right. Considering the design parameters, Q for the electrical oscillator is given by omega prime L by R. Okay, all right. So, well, if you a little more, if you just try to visualize, all right. Well, you see, if you just try to find out the power dissipated over here, if you consider in terms of power dissipation, if you try to study the whole thing, if P is the rate of loss of total energy, that is power, isn't it? the rate of loss of total energy. If we say that this is P, then this is equal to, what can we say about this? This is equal to minus of dE dt, which is equal to twice K, because it's a loss. This sign signifies loss, okay? Or otherwise for your calculation you don't have to consider this. 2K E0 e to the power minus 2 kt, isn't it? So that is equal to twice Ke, isn't it? So, well, you can say that minus of dE, if you consider minus of dE, what is minus of dE? Minus of dE is equal to twice Ke dt. Now what is this equal to? This is equal to, K is equal to R by twice M, 2 into R by twice M E dt. So that will be equal to R by M E dt. What is dt? Let us put this as, well, let us consider this dt. Let us consider this dt as equal to dt. What is t? T is the time period of the oscillator. So, in one time period, dt equal to t, what do we get? So, for dt equal to one complete time period t, what do we get over here? This is equal to 2 pi by omega prime, isn't it? So, minus of d e t is equal to, so basically minus of det, what is this? It is the loss of energy during the time of one time period, or loss of energy per cycle. Okay, so this I am calling as the loss of energy per cycle. All right, so this actually will be equal to, what will it be equal to? The loss of energy per cycle. This will be equal to R by M E T, which is equal to R by M E 2 pi by omega prime. All right, okay, so what do you get from here? From here you get omega prime M by R is equal to minus of 2 pi E by d E t. Okay, so again, therefore, you define the quality factor Q as Q is equal to 2 pi times energy of the oscillator, divided by the energy lost per cycle. Energy lost per cycle. So this is what is very important for you to know. But how you are getting it, just to get a feeling of how you are getting it, I have described all those things before. But you need to know that the quality factor is 2 pi times the energy of the oscillator divided by the energy loss per cycle. Okay, all right. So let's stop over here. Okay, and let us try to finally find the relationship between logarithmic decrement, relaxation time, and quality factor before we complete the class.